This presentation will present medium temperature and low temperature defrost systems. Before we begin though, we need to take a look at solenoid valves because some of the refrigeration systems used in this presentation will require the use of a solenoid valve. So we need to take a look at what the solenoid valve involves so we understand how it works when we get to the actual refrigeration system. The next slide will present a cutaway or exploded view of the valve. Here's a solenoid valve by Sporting Company. Have the magnetic coil. There's going to be a plunger, and you'll notice inside the plunger there is a spring. There is a needle with a seat. There is a flow direction. Solenoid valves will flow in one direction only. And there is a manual lift stem. Now when you look at the base of this particular solenoid valve, we do see a nut that if we take the nut off, we would expose a manual lift stem. If there is no nut, then there is no lift stem. So some solenoid valves provide a convenience that if you want to open them, you simply take off the nut and crank the stem in, and that will open the valve manually. Some do not have that feature. Here we see the solenoid valve again and the magnetic coil, the plunger housing, the plunger with the needle, the seat, and the valve body. The solenoid valve operation is such that when the magnetic coil is energized, that will lift the plunger. Then fluid will flow through the valve. When the magnetic coil is de-energized, the plunger closes by spring pressure on the top of the plunger. Let's take a look at that then. Here we're going to look at an exploded view again, and we see the plunger and the seat being removed. But let's take a look inside the solenoid and valve now. When the magnetic coil is energized, the plunger magnetically is pulled up into the center core of the magnet. You'll notice that the valve seat then is taken off of this valve seat, and fluid flows. It doesn't matter what the fluid is. We're going to be dealing with refrigerant flow. It could be water flow. Now we see the power is turned off. The plunger is going to drop. You see the spring is going to push the valve closed, and the fluid will stop. So it's one direction. It's not a check valve in the sense that a check valve is one flow also, but this one is electromagnetically operated. The most common application for a liquid line solenoid valve is what is known as pump down. So let's take a look at the pump down operation first, and then we'll move on to the defrost cycles and circuits. We're going to need a liquid line solenoid valve. You'll notice its location obviously is in the liquid line. That's why we call it a liquid line solenoid valve. So it is a solenoid valve that is in the liquid line. Therefore, it is a liquid line solenoid valve. Later on in this presentation, we're going to be looking at another solenoid valve that is put in the hot gas line. It will be called a hot gas solenoid valve. But back to the liquid line solenoid valve. We see that a thermostat is going to be controlling the liquid line solenoid valve, and that the low pressure control is going to be controlling the compressor. So the thermostat does not control the compressor directly. It controls it indirectly based upon the pressure that the low pressure switch senses. Let's look at the sequence of operation. First of all, the thermostat is currently calling for cooling, so the compressor is operating. You'll notice that from the liquid line solenoid valve to your left, there is red liquid. Coming through the metering device, we see the blue liquid vapor going back to the compressor. There is pressure shown on the pressure gauges on the low side and high side of this compressor. Now we're going to look at the thermostat being satisfied. It doesn't need any more cooling, so it's going to de-energize the liquid line solenoid valve, and that's going to shut off flow of refrigerant, and you can see that the compressor is continuing to run and take all the refrigerant out of the low side and put it over on the high side. Then the system continues to pump down, and as it does, the suction pressure is going to fall. At some point in time, we have adjusted the LPC to open and turn off the compressor. And the compressor is shut off, and you'll see the high side pressure now is dropping to the temperature pressure of the ambient that the condenser is sitting in, located in. As the temperature rises in the box, we're going to find that the thermostat again says I need to be cool. So I'm going to open the liquid line solenoid valve. It's going to energize it, and when it opens, you're going to see the refrigerant flowing. And when the refrigerant flows from the high side through the meter device to the low side through the compressor, the pressure will build back up, and the LPC will once again close and bring on the compressor. LPC closes, compressor begins to operate, and we are back into the refrigeration mode of operation, the on cycle. So this is known as a pump down operation. So we pump down concept is that we close the liquid line solenoid valve and pump down the low side of the system. This is not to be confused with pump down, meaning evacuation, when you take the refrigerant out and you evacuate and you pump down into a deep vacuum. So there's a couple different definitions to pump down. In this case, we're pumping down the refrigerant out of the low side, putting it over on the high side, so that the LPC then is controlling the compressor. Okay, let's move on to defrost now. First of all, medium temperature and then low temperature. Medium temperature, there are two types of medium temperature defrost. One known as random off cycle, another one known as timed off cycle. First of all, the random off cycle. Medium temperature refrigerators use the off cycle to melt frost accumulation. That is, when the compressor is not operating, the evaporator will warm up to the space temperature and the ice will melt off the coil. Now remember that the evaporator is always 10 to 20 degrees colder than the space. So if we have a space of 35 degrees, the evaporator is operating at 15 to 25 degrees. So frost will accumulate on that evaporator. But when the compressor turns off, the evaporator will warm up to that 35 degree space temperature and the frost will melt off. The run time of the equipment is not predictable, so melting the ice off the evaporator is going to be random, depending upon the time the equipment is off. Now, a timed off cycle is if the refrigeration equipment does not have enough off time to warm the coil to the space temperature, then a timer will be used to extend the length of the off cycle for the evaporator to warm up to the space temperature and then melt the ice off the coil. There are several reasons for that, and we will look at that shortly. This extended timed off cycle will not have an adverse effect on the product temperature. Now, in order for that to happen, we need a defrost clock, and there are two types of clocks for commercial refrigeration. One that would be used for medium temperature applications, and one that is used for low temperature applications. So let's take a look at the medium temperature clock, and then we'll move on to the low temperature clock. Here we're going to be looking at a walk-in refrigerator, meaning that we're at 35 degrees to 40 degrees approximately, with a pump down solenoid refrigerating cycle. And this will be for random off cycle. Now you'll notice the neutral is brought into a junction box, and from the junction box it goes to the evaporator fan. We bring power in off of L1 and we go through the junction box for our wiring connections and onto the fan, and you'll notice that the fan is what we would call hot wired. There is nothing in that circuit to break the power going to the fan other than the on-off switch, which is not shown here, a disconnect switch somewhere. So in commercial refrigeration, the fans run 100% of the time. Now we're going to take a neutral to the solenoid valve, bring our hot wire to a thermostat, which is then going to the liquid line solenoid valve. The solenoid valve is open. We're calling for cooling, so you can see the refrigerant is flowing through the coil and out to the compressor. During the off-cycle defrost, what will happen is the thermostat is satisfied. power is off at the liquid line solenoid valve, it will close, and you'll see that the refrigerant is pumped out and moved over to the high side, as we saw in an earlier screen. Now, some equipment does not use a liquid line solenoid valve in this type of application. They simply use the thermostat to control directly the compressor. Either way, we end up turning the compressor off for a period of time, and it will be random depending upon the use and the application of the refrigeration unit. Let's look at the time clocks. Now, you could say that it is a common time clock because this time clock can be used for cycling outdoor lights, for heaters, and many different applications. The clock in this example has one set of normally closed contacts. That's all it's required. It is going to cycle the refrigeration compressor for an extended off cycle. So here's the time clock. This particular model is 115 volts. You can get them for 230 volts. You'll notice that you have L1 coming into the terminal on the left. 4 terminal on the right has neutral connected to it, so there's your 120 volts. You'll notice that between terminal 4 and terminal 3, the neutral comes into 4 and goes out of 3, just a junction point. You'll notice the normally closed switch is going to be between terminals 1 and 2, the brass terminals. So terminals 2 and 3 would go out to the load. 2 would be the L1 side, 3 would be the neutral side. You're going to have a dial. It's going to rotate clockwise. In fact, if you look at the pointer in the middle, the black round circle that has a pointer on it, just above and below it, you'll see the red arrows pointing clockwise. So if you wanted to rotate this particular time clock, you would have to rotate it manually clockwise, and it will also rotate clockwise during its operation. There is a time of day pointer. Right now it's pointing to 8:15. That says morning, so that's 8:15 a.m. The trippers, there are 2 of them. One is going to be for off at 2 a.m. Now, if you notice what happens down at the L1 to load connection, when the timer comes around to 2 a.m., it's going to open a set of contacts and the load will stop, in this case, the compressor. And then it'll come back on at 4 a.m. So if you look down at the L1 set of contacts, when we get past 4 a.m., the timer will mechanically close the contacts and the compressor will be allowed to operate based upon either the LPC or the thermostat. There's also an override switch so that if you were on the job and you wanted to turn this compressor on or off, you would be able to flip it with that switch there. Continuing on with the time clock and refrigeration, we end up with a planned off-cycle defrost. This gives the evaporator extra time to air defrost. The clock shuts off the compressor while the evaporator fans continue to run. So here we see the same system, but now we're going to be looking at not a random off cycle, but a timed or planned off cycle. The defrost clock, timer motor, we have our contacts between 1 and 2. We have our neutral. Neutral goes up to the timer motor. We would need to change the wiring, take L1 off of the thermostat, bring it to terminal 1, and that would go on internally to the timer motor so it can be running 100% of the time. As long as the power is on, this timer motor will be advancing. Then terminal 2 would be then wired to the thermostat. Now the planned off-cycle defrost would be such that when the contacts open, let's say 2 a.m., you can see that we would kill the power to the thermostat and we would go into the pump down cycle. Or we could control the compressor directly with the thermostat. And we see the circuit open. Now at 4 a.m., if that's when the timer were set, at 4 a.m. the contacts would close between 1 and 2, and we would be allowing the compressor to run for the next 22 hours based upon the thermostat. Compressor is going to be off for the 1 to 2 hours. The evaporator will air defrost. Refrigerator planned defrost. Now, there is a need to plan for more off cycles. When? For example, we looked at one cycle being off for 2 hours, one off cycle being 2 hours. You may need to plan for more off cycles when the medium temperature box is 34 to 36 degrees. So the colder the box, even if you have a planned off cycle, 34 degrees is not that much above 32, so there still may not be enough off time to warm up the coil and defrost the coil. If you're running the box at 40 degrees, then that would not be an issue, or should not be an issue. If the box is in heavy use or there's a high product load, possibly someone has opened the box, put in a large warm product, a large amount of warm product, and now that's going to make the refrigeration unit run for an extended period of time, and the ice is going to collect a lot faster, and it may not have enough off time, even planned off time, to de-ice. The same thing with heavy use. Maybe your product is at 34 degrees, but you're in and out, in and out, in and out of that walk-in refrigerator so much that the runtime is extended during, even though the 22 hours, when it's off for 2 hours, it still may not be enough planned off time to de-ice the coil. Then you would need to have additional trippers to put in on the timer to extend that off time to different times of the day. The clock will stop the compressor no matter when you tell it to, based upon that tripper. Again, the fans continue on medium temperature application. The fans are going to continue to run on the refrigeration equipment regardless of what's happening at the compressor. There's going to be a 1 to 2 hour off time, and all the frost is going to melt off the coil. Note, schedule when the box is not in use, usually the middle of the night, between 12 a.m. and 6 a.m. is when the box probably is not likely to be in use, or at least the minimum amount of use time, and that's when you'd want to shut down the compressor. Let's take a look at how that's going to work. You'll notice here we have a coil that's all frozen up. We have a space temperature of 35 degrees. A random off cycle now sometimes does not melt all the frost. So we're going to use a clock to schedule a longer air defrost time. The clock shuts off the compressor, usually at night. The compressor will be off 1 to 2 hours. The fans do continue to run. The coil rises to 35 to 38 degrees. And you'll be seeing that happen. All the frost will melt. So you'll notice that we're warming up from the 20 degree coil temperature to 35 degrees, and as the coil warms up to 35 degrees, the ice will be melting off of it. And now we'll be ready for the next on cycle, the next freeze cycle. The coil will be clear. Moving on to low temperature applications, low temperature evaporators, which are freezers below 32 degrees, we're operating for the actual space temperature. These are similar to other evaporators except that defrost needs heat. We're going to be using a wider fin spacing on freezers than medium temp, high temp, and air conditioning systems. We're going to be looking at frost buildup on freezers. It's naturally going to happen. You're below 32 degrees and the frost is going to build up on it. Frost will be normal for refrigerators and freezers, and as the unit runs, the moisture will be collecting on the refrigerator and the freezer. Now in a refrigerator, light frost can air defrost. Now you're noticing there's a certain amount of frost on here. The coil is certainly not a whole lot of frost on it, therefore we call it light frost. Well, freezers need heat because you can see we now no longer have light frost, we get heavy frost accumulation because of the lower temperatures we're operating at. The fin spacing means how many fins there are per inch. On freezers, you're going to find 4 to 8 fins per inch, wide spacing. Refrigerators are 8 to 12 fins per inch. When you get to air conditioning, you'll be looking at 12 to 20 fins per inch. Here we see a measurement of the fin spacing, and in that freezer evaporator, we see 1 inch and 6 fins. Here we see the coil all frozen up, all frosted up, and we need to defrost it. The sequence would be that we would bring on a defrost cycle, and that's going to turn the frost to water. And we see that the heat is melting the frost and it's going to turn to water. Then after defrost, we would go back into a freeze cycle. But the problem is that the fans will not begin. They are not energized. It says they will begin, but the fans are not energized for a while to prevent blowing of water into the box. Now remember, you have a wet coil. There's a lot of moisture in that coil. It's stripped off. Not all of it has come off. You bring on a fan, and the fans now are going to blow that water out into the box. That'll land on the frozen product, land on the frozen floor, and there'll be ice on the floor. That doesn't bode well for a safety situation. So we're going to keep the fans off until the coil gets below 32 degrees. Once the coil gets below 32 degrees, any residual leftover water on the coil will refreeze. Then when we bring the fans on, there is no water to blow out into the space. So that'll be the sequence as we work through the rest of this material. Low temperature defrost. A freezer requires some heat to help defrost the evaporator. The heat can be either electric heat, which would be applied externally to the coil. You could use hot gas heat, which would be applied inside the coil. There would need to be defrost termination. Termination means that controls are required to stop or terminate the defrost and return the system back to the freeze mode of operation. And you would need some type of control scheme to delay the fans. And part of that process would require a clock to control both the defrost and the freeze cycles. On electric defrost sequence, we're going to take a look at that first, then we'll move on to the hot gas. On the electric defrost sequence, the defrost is initiated by a time clock. So we say it's time initiated. So the defrost sequence is time initiated. The fans are shut off on the evaporator because once your source of heat is energized, you don't want to keep the fans on, keep blowing cold air over the coil as you're trying to de-ice it. So the fans are turned off. The source of heat is going to be energized, in this case electric heaters. The ice will melt off the coil. Then defrost is terminated by temperature or time. Now, you really want to terminate on temperature. You really do not want to terminate on time. Time is there simply as a backup safety in case the temperature sensor should fail and not allow it to come out of defrost. So again, you want to be time initiate, temperature terminate. You don't want to terminate on time. Time is a safety backup in case temperature terminate fails. We've got to get the heaters off. Then the source of heat is going to be de-energized. And the compressor will come back on. We're back into freeze mode of operation. Now the evaporator fans are delayed from coming on until the coil temperature drops below 32 degrees, and usually that's around 25 degrees. So my temperature sensor, my temperature control is set to trigger the fans back on at around 25 degrees. Here is the end of the coil. We're looking at the end of it where there is electric heaters. You can see the electric heaters being fed through the coil on the side view here. We have the defrost terminator. The fan delay is going to be a single pole double throw switching action. Temperature controlled. Single pole double throw, temperature activated. There is a heater safety. In this particular application, not every application has the heater safety on it. Again, we depend upon time as the backup safety in some cases. So if we have time as a backup safety and including this heater safety, we have a redundant system. The wiring terminal board, where all the wiring connections are made. And now we're going to be looking at the freezer defrost clock. We're going to be looking at the front view, which is the left half of the screen, the rear view, the right half of the screen. You'll notice that there are defrost pins. 2 of them are pointed out here. There is a third one also shown. That would be the time that the defrost will occur. In this case, it is going to be 4 p.m., midnight, and 8 a.m. Where it says time, and that pointer, that would be the actual time of day on the dial. There's a fail-safe setting. You'll see that little copper type pointer, and it's pointing to 46 minutes. So it's set for 46 minutes. The way that's adjusted, you'll see some teeth there. You push down on it and you move it to the left or to the right. That will be the backup safety. There's going to be what is known as a defrost solenoid. You'll notice the defrost solenoid, it has the coil, the black coil. The plunger is hanging out of it, and it has a notch on the end of the plunger with a pin in there. So that is the defrost solenoid. There is a slide, which we're going to take a look at shortly. The slide will go to the right and back to the left. There is a defrost clock. There's also, right below the word slide, there is a set of contacts shown. 2 sets of contacts, actually. And we're going to be looking at those here also. Again, another view of this where we see the solenoid being energized, if you will. The slide will go to the left and to the right. And we're going to see how that works. Here's the contacts. One, you'll notice the contacts on the left is closed. The contacts on the right, where it's pointing to contacts, that one is open. So the slide will go to the left. That when it does that, it closes the contacts on the right, opens the contacts on the left. Now listen to that. The slide will go to the left. The timer comes around, there's a cam in there, and the cam will move the slider electromechanically. It'll mechanically move the slide to the left, close the set of contacts that's open, open the set of contacts that are closed. That'll initiate defrost. And we're going to look at that in a minute. That'll initiate defrost. When we come out of defrost, the solenoid is energized. That plunger will pull up into the solenoid. I pointed out to it that there has a little pin sticking in that notch. That pin will be lifted and will disengage the slide so that the slide can move back to the right. When it moves back to the right, the normally open contacts will go back open. The normally closed contacts, as shown, will go back closed. So let's go back through that. The timer motor with the cam is responsible to move the slide physically from right to left to change the position of the contacts. But at the end of the defrost, the solenoid is the determinating factor, which will lift its pin and disconnect the slide from the cam so that it can slide back to the right. All right, let's go through this as we work through the material here. Defrost settings and wire terminals. The clock on the next slide is scheduled for defrost in 24 hours. The fail-safe time setting is a backup to the defrost termination switch. I mentioned that previous. If the defrost lasts too long, about 45 minutes on the sample clock, in other words, the fail-safe time on the clock you're going to see on the next screen is set for about 45 minutes. If the defrost lasts longer than 45 minutes, the fail-safe will put the system back into freeze. It'll override the defrost terminator on temperature, and time will send it back into freeze mode. So here we go. A typical time clock is this Paragon 8145-20, very typical one. We see the dial here, which is the clock time. And we see pins at 4 different locations, what is known as the defrost trippers. What that means, those are the times when it will trip it or turn it into defrost, turn on the defrost. And the time pointer is the time of day. The inner dial is showing the fail-safe time. Notice the arrows. In this case, we want to turn this time clock counterclockwise. If you remember on the previous screen, the timer was turned clockwise. So you must look at the dial to determine which direction the dial needs to be turned. So let's go back to the fail-safe time. You'll see the pin here is at about 48 minutes or so, 46 minutes. That's the fail-safe point. Freeze is terminal 4. Defrost will be terminal 3 on this particular timer. So freeze will be energized, terminal 4, terminal 3 will be de-energized. When you go into defrost, terminal 3 will be energized and 4 will be de-energized. You'll notice between 1 and 2, terminals 1 and 2 are exactly the same terminal. We bring the hot wire into terminal 1, that would be L1, and it has a jumper piece of copper that jumpers over to terminal 2. So what comes into 1 goes to 2. Neutral, you'll see, is connected to the end of the line. So power comes in to 1 and 2. Neutral would be common or the reference wiring. Terminal X is going to, in this timer, to the defrost terminator. Now, setting the time. Sometimes the defrost clock has to be reset for the proper time of day. Power goes off, somebody turns the power off, you need to reset it. You set the time by turning it counterclockwise. And assuming it's 6 p.m. when you're on that job and you're done and you're leaving it, you'd want to make sure it is set at 6 p.m. Now let's move forward on a defrost clock and the wiring. The following slide is a pictorial diagram of the clock, the evaporator, and the controls. The color-coded wiring as illustrated is pretty typical of most walk-in freezers, and the sample system is in the freeze cycle. So we're going to be looking at the wiring diagram for a walk-in freezer with electric defrost and remote condensing unit. There's the slide, our clock motor, the defrost solenoid, there's our defrost heater, we have the evaporator fan, the thermostat, the liquid line solenoid valve. We're going to need a drain line heater. Remember, you're below 32 degrees in the space, so the water coming off of the coil is going to go into a drain pan as well as a drain line, so you want to make sure you put a heater on it. There is a defrost termination fan delay. Has 3 terminals on it, red, brown, and black. Notice we're bringing power in L1 to 1 and neutral to N. And that is going to the time clock. So as long as power is applied to this timer, the time clock will be advancing. It's hot wired, the motor is. Now terminals 3 and X go to the defrost solenoid. Terminals 3, 4, X, and N are representing the end of the coil, the actual evaporator, in the location where the freezer is. So this would be the terminal board where the wires would be connected. 3 in this case would go to 3. 3 would go to the defrost heater. 4 is going to go to 4, which goes several places. 1 to the evaporator fan, 2 to the defrost drain heater, and 3 to the thermostat. Now, we're seeing the drain line heater being controlled during the freeze mode. Many times you find the drain line heater simply hot wired. It never turns off. In this particular case, we're going to find that the drain line heater is energized during freeze mode, de-energized during defrost. Again, different ways of doing things. N for N. N goes to R of the defrost termination relay, goes to the drain heater and to the heater and to the solenoid valve. Now we have a single pole double throw temperature activated device. It is now in the R to black position. This would be the cold position, what would be referred to as the cold position. That's the 25-degree position. The black wire would go to, or the black terminal would go to the fan. The brown wire would go to X. X of the terminal strip goes to X of the time clock, which goes to the defrost solenoid. So the brown terminal would be considered the warm terminal, the 55-degree terminal. In other words, it gets up to 55 degrees. We'll see that after a bit. R to black will go to R to brown. So we have a cold position and a warm position on the defrost termination fan delay. Let's move on to the defrost clock and the heaters. Defrost is time initiated. The clock movement pushes the slide bar on the rear of the clock, so the clock movement, the mechanical linkage, will push or move that slide bar. The slide will change the switch contact positions from freeze to defrost. So let's take a look at that. We are going to be going into the defrost cycle. Notice 1 to 3 is open, 2 to 4 is closed. We're going to start the defrost. When we start the defrost, the timer comes around. The camming action will move the slide as shown. It'll open 4 and close 3. So terminal 4 is open, terminal 3 is closed. Now when terminal 4 is opened, that's the freeze terminal. Notice what happens. The thermostat power is killed, so the liquid line solenoid valve is closed. That means that the compressor will continue to run until the low side is pumped down to the low pressure switch pressure, and that'll turn off the compressor. At the same time, we see the drain line heater being turned off, and the evaporator fans are turned off. Fan or fans if there's more than one. You'll also notice now that terminal 3 is closed between 1 and 3, so now we have power that's going to go to the defrost heaters. So the heaters are now on. So it's time initiate. So the clock motor advances, moves the slider, mechanically moves that slider so that we de-energize the freeze cycle and energize the defrost cycle. Now notice 3 also sends power up to the defrost solenoid. I'll say that again. Notice that 3 sends power to the defrost solenoid, but on the other side of the defrost solenoid going to terminal X, we have a dead end street when we get to the defrost termination fan delay brown terminal. So my defrost solenoid is not energized yet. Now at the end of defrost, meaning that the evaporator warms up to 55 degrees, notice what's happening. My defrost terminator goes from its cold to its warm position. When that happens, terminal brown is energized, which activates the defrost solenoid. Now when the defrost solenoid is energized instantly, we're going to see the slider go the other way, and we're going to take a look at that in a second. We're going to switch back from the defrost into freeze mode. Now when the defrost termination switch is warm enough, usually around 55 degrees, the clock's defrost solenoid is energized. That's the clock's defrost solenoid. That's not the liquid line solenoid valve. We're talking about the clock's solenoid. And we call that sometimes the timer release solenoid. It's called the defrost solenoid, or it could be the timer release solenoid because it releases the timer from its responsibility of being in the defrost mode. Now let me say that again. The timer release solenoid is a solenoid inside the clock that releases the timer from its responsibility of going into the defrost mode. Remember, we're in the defrost mode. So it's going to release its responsibility. And let's take a look at how that happens. What's going to happen is the solenoid will now mechanically move the slide, switching the contacts out of defrost and back into freeze. The fans will not come back on until the temperature of the evaporator gets colder, which in this case we're looking at 25 degrees. So we have closed, 1 to 3, 2 to 4 is open. Notice the defrost terminator, The defrost terminator is now in the warm position, so we're continuing that process. Now, notice the energized solenoid will release the timer from its responsibility of being in defrost. The slide will now move to the left, as shown here. That will break the defrost cycle and make the freeze cycle. So we see terminal 3 being de-energized, heat is returned off. So we have time terminate. Remember, time initiate, time terminate. And terminal 4 will now be closed, and that will send power to the fan, but it cannot come on because it's broken at the black terminal on the defrost termination fan delay. Power will be sent to the defrost drain heater. Well, we need to make sure we keep the drain warmed up now that we got water in it. And the thermostat now, notice what's going to happen. It's going to energize, and the liquid solenoid valve is going to open. The refrigerant is flowing through the low side. The LPC senses an increase in pressure, and the compressor comes on, and we are now back into freeze mode of operation. But the fan is not on. Fan or fans are not on in the evaporator. Remember, if we bring those fans on right away, we're going to blow the water off the coil right into the space on the frozen product and on the frozen floor. So we're going to delay that until the defrost terminator / fan delay gets back to its cold position, meaning when the evaporator gets to 25 degrees, then we drop to the cold position and the fans are now brought on. And we are now into full-time freeze. Now that may take 5 to 10 minutes for that coil, or longer, depending on the size of the coil, for those fans to come back on at the end of the defrost cycle. Pretty interesting circuit, quite actually. All right, the last thing we want to take a look at would be the internal heat, which is your hot gas defrost. We're going to use the hot gas coming from the compressor discharge. We're going to put that hot gas right into the inlet of the evaporator. So we put heat on the inside of the evaporator, it's going to melt the ice on the outside of the evaporator. So we have defrost from the inside out as opposed to electric heat, which was outside. We have hot gas defrost, and we have frost buildup. Now we've not gone into defrost yet, but we're into freeze mode of operation. We have frost built up on a coil. We need to get that cleaned off for efficient coil operation. So we're going to be using a hot gas solenoid valve. Now remember, it's a solenoid valve that's connected to the hot gas line. Therefore, we call it a hot gas solenoid valve because of its location. Now it's going to be piped into the inlet of the evaporator. The valve will open under defrost circumstances, and you'll notice what happens. The hot gas is coming through the hot gas solenoid valve. It's being dumped into the inlet of the evaporator after the TXV. And the refrigerant is going to warm up, the coil is going to warm up, and the ice is going to be melted off the coil. One passing comment here is look at the device at the compressor. A crankcase pressure regulator would be required on this application because we are subjecting the low side of the compressor to high pressure during defrost, and we will overload that motor very quickly if we do not limit the back pressure at the compressor. And that's a hot gas solenoid valve or hot gas defrost system. Fairly simple. This ends the defrost circuits for medium temperature and low temperature applications.